And we are finally getting to the stoichiometry part of the chapter. So this part 5 video, we're going to put together the unit factors we've used to this point, as well as add one more, and then do stoichiometry. So just a reminder, the definition of stoichiometry was at the beginning of the chapter, which was like a million years ago. But stoichiometry is when we're comparing amounts of chemicals as part of a chemical reaction. So it's letting us do things like predict how much product we're going to make, or predict how much reactant I need to mix together to get to a certain amount of product. Okay, so that means we have to include balanced chemical equations into our math. That's a thing we have not put together yet. Up until this point, the unit factors we've used, we've been comparing one chemical to itself. I have grams of carbon monoxide. How many moles is that? Or I have molecules of silver chloride. How many moles is that? Or I have grams of sodium nitrate. How many molecules is that? We've done a lot of, the empirical formula was doing a lot of grams to moles. But we're going to now have to compare one chemical to another. If I want to make this much gold, how much gold to chloride do I need to start with? Okay, so that new unit factor is called the mole ratio. So what we have up at the top where it says equation, I have a balanced chemical reaction. This can be considered a combination reaction. It could also technically be considered a combustion reaction. I know it's missing the CO2 at the end, but there are no carbons in here at all. So to be balanced, there's a coefficient of 2 in front of the H2, a coefficient of 1 in front of the O2, and a coefficient of 2 in front of the H2O. And when we started balancing reactions, I called these recipes because it's telling us, all right, I need 2 molecules of hydrogen to be mixed with 1 molecule of water. Mix, pour them in the bowl, stir it up. What would really be happening is a chemical reaction there. And then what I'm going to make, what pops out of the oven at the end, are 2 molecules of H2O. Okay, so it's a recipe. Well, the mole ratio is just using that recipe to compare. Okay, so again, I said it this way. 2 molecules of hydrogen and 1 molecule of oxygen are going to react together to make 2 molecules of H2O. This is just looking at their average atomic mass in AMUs, where it's just looking at the AMUs of those. And then here's where it gets interesting. That ratio, the 2 molecules to 1 molecule to 2 molecule, that also works for moles. And moles is kind of our unifying unit. We turn other things into moles, so we can compare them. So 2 moles of hydrogen to 1 mole of oxygen will make 2 moles of H2O. Okay, and then this is just looking at the molar mass. Okay, so mole ratio, what we're going to be doing is you look at a balanced chemical equation. So this is our example. And we can compare the ratio of any 2 chemicals. If we're doing a ratio, that's a fraction. So we need a numerator and a denominator. We're going to compare 2 chemicals. So let's compare oxygen to water. So in this reaction, I want to know, how do these 2 chemicals compare? Well, based on this balanced equation, we know there's a 1 right there, right? Well, for every 1 mole of oxygen, I'm going to make, oh, come on, pen, 2 moles of H2O. And just like any unit factor, I could flip-flop top and bottom. Okay, awesome. That's a mole ratio. Well, maybe I don't care about oxygen and water. Maybe I care about oxygen and hydrogen. Well, looking at the balanced equation, 2 moles of hydrogen, and the way I know it's 2 is I look at the balanced equation and I'm looking for the coefficient in front of it. 2 moles of hydrogen, 2 if I'm comparing to oxygen, are we good that even though we don't see anything, that's like a 1? 1 mole of O2, which I could write that, 1 mole of O2 on top, 2 moles of hydrogen on the bottom. And then I could also compare, the one thing I haven't compared yet, are hydrogen to water. Well, 2 moles of hydrogen to 2 moles of H2O, which could also be written 2 moles of H2O to 2 moles of hydrogen. These are unit factors, so they're going to be used to cancel out something. So you will choose which version of the fraction, if you put hydrogen on top or bottom, based on your calculation. This will be a unit factor in the middle of a calculation. So you'll choose your two chemicals based on what the question is asking about. The number of moles is entirely dependent on the balanced chemical equation. So this unit factor changes every time we do a different chemical reaction. It also changes depending on which two chemicals the question is asking about. So unlike Avogadro's number, where that unit factor can very clearly say 1 mole equals 6.022 times 10 to the 23rd of things, where it's like written out there. The only thing that changes are the molecules or the atoms, or the things. Kind of like molar mass, where it says 1 mole equals molar mass, where you got to plug a number in there that you figure out or that's given to you in grams. For a mole ratio, I don't have a great way of shortening that. So I'm going to go back and we're going to rewrite our unit factors so far. So I just said them out loud, but I'm going to say them again. 1 mole is equal to 6.022 times 10 to the 23rd things. This is the unit factor we use when we're counting atoms or molecules. The second unit factor, which we've actually used a lot more, 1 mole equals the molar mass in grams. And just a quick reminder, that number comes from the periodic table, adding together all the pieces. And then our brand new unit factor, what I'm going to write here is just the phrase mole ratio. The mole ratio is going to be, I don't really have much to write. Moles of one chemical equals moles of another chemical. And what chemicals they are, it's going to change for every question. The number of moles changes for every question. So what I'm going to write is just from balanced equation. Okay. So in true chemistry fashion, now that we have a brand new unit factor, let's jump into using it. And when we use this mole ratio unit factor, most of the time, these two unit factors are going to show up in the same question. So we're going to jump into that. And just so you know, anytime you use a mole ratio, that technically is the sign that you've just done stoichiometry. So stoichiometry is doing math involved in a chemical reaction. That mole ratio comes from a balanced chemical equation, which is a chemical reaction. So stoichiometry is just when you use the mole ratio. You're never going to have to decide, like, is this stoichiometry or not? Do the problem. It doesn't really matter, but I'm just pointing out that you haven't done stoichiometry yet, technically, because you have yet to do a mole ratio. So our textbook loves its flowcharts. Okay, so most stoichiometry calculations in chapter 3 are going to be what we call mass stoichiometry calculations. That means the question's going to give you grams, which is a mass, and it's going to add grams of one chemical, okay, which is a mass, and it's going to ask you to solve for grams of a different chemical, which is another mass. So you start with a mass and you end with a mass. This little picture is their visualization of how the steps it's going to take to get from the grams of the one chemical to the grams of the other chemical. All we're doing are using those beautiful 3 unit factors that we just wrote down and basically doing dimensional analysis, canceling out our units. I would not recommend like memorizing this, because what's going to happen is we're going to get to chapter 4 and we're going to add a new unit factor to this process. So just, if it's helpful for right now, that's great, but you need to get to the point where you can solve these problems without referring to this picture. So I made the picture bigger just in case that helps you in any way. So this first example, I'm going to do it exactly how the textbook did it, which means they literally did the calculation following this U shape. I just, it is what it is, okay? And then on the next slide, I'm going to redo the same problem, just the way that I like to write them, like in one line, canceling out the units. Okay, so here's the way the question looks. We need to determine the grams of water produced from 1.00 grams of C6H12O6, so sugar. So there's the balanced chemical equation. Okay, so we need to determine the grams of water produced from 1.00 grams of C6H12O6. So what I would normally do is write down grams of water on the right-hand side, and then write 1.00 grams C6H12O6 on the left-hand side, and then start doing unit factors. Now, if we're going to follow that U-shaped thing, the first thing it said is molar mass. So what they did was they took the molar mass of C6H12O6 and wrote it there.
Box is you.
Okay, thank you, baby.
But not all the scooter.
Okay, not the scooter. Okay, thanks.
I wish the scooter's you.
I know.
But we did 3 days. I don't know why.
Baby, shh.
I don't know why it's
Shh.
3 days.
Griffin, shh. I'm recording your video. Shh. Okay. All right, so we did our molar mass. The next thing that picture says is mole ratio. So the mole ratio would be between the two chemicals that they mentioned, which is water and C6H12O6. So the mole ratio is a 1 to 6, and that goes there. And then the last step on this U-shaped is a molar mass. So we'd use, in this case, the molar mass of H2O, and we got to our answer. So now I'm going to redo this question, doing it my way, not in a U shape. So now we're going to do it my way. Sorry, all this, if there's commotion in the background, my two kiddos have been sharing one scooter that was made for like a 5-year-old. So my 8-year-old was like smushing it. And they just got the bigger scooter in the mail, and it's amazing and the best thing that's ever happened. So if there's excitement, that's why. Okay, so the question, which I didn't carry over here, was what was the mass of water produced starting with 1.00 grams of C6H12O6. So just like when we did our dimensional analysis stuff in chapter 1, first thing I do, read the question, figure out what we're solving for. The question said mass of water, so I'm going to say grams of H2O. Second, what are we starting with? What were we given? 1.00 grams, C6H12O6. And the next are just unit factors. So we have 3 unit factors we've learned in chapter 3 so far: Avogadro's number, molar mass, and mole ratio. One of those 3 has the unit grams in it. And I know that that's going to be the one I want first, because our first job is to cancel out the unit we're starting with. So I need to use the molar mass of C6H12O6 here. So I would look up, I'd add together 6 carbons, 12 hydrogens, 6 oxygens, and I'm going to tell you it's 180.15588 grams of C6H12O6 in 1 mole. Now, what I don't want you to do, people get excited about now that we know the mole ratio, and so they start changing this number. The molar mass unit factor very clearly says 1 mole equals the molar mass in grams. That's the unit factor for molar mass. That is not impacted by the balanced chemical equation. Molar mass is always going to have 1 mole in it. Okay, so I can cancel out grams. So what I have now are moles of C6H12O6 that I need to cancel out. So I know whatever unit factor goes next, that's going to have to go down here on the bottom. But if you look at our unit factors, all 3 of our unit factors contain moles. So thinking through this, do I want to convert moles to molecules? Does that help me in this situation? No. Do I want to convert moles of C6H12O6 into grams of C6H12O6? Nope, because that's what I just undid. So that leaves me with the mole ratio. I know in my mole ratio that moles C6H12O6 are going to go on the bottom, so it will cancel. And then I just have to decide which chemical is going to go on the top. Well, the other chemical the question asked about, which is water. That's how you decide which 2 chemicals to look at. So to get the numbers that go there, I'm going to look at my balanced equation, find C6H12O6. It's like a 1. Look at my balanced equation, find H2O. There's a 6. And I have this set up so moles of C6H12O6 will cancel. I did not plan my space well. So now the unit I have left is moles of water, which is glorious, but what I need to solve are grams of water. So of my unit factors, molar mass lets me do that. So 1 mole of H2O is equal to 18.01528 grams of H2O. That cancels. So looking at my answer to do sig figs, well, this has 3 significant figures. The molar mass has 1, 2, 3, 4, 5, 6, 7, 8 significant figures. The mole ratio is an exact thing. These are perfect whole numbers, so infinity sig figs. And this one is 1, 2, 3, 4, 5, 6, 7. So my answer, well, 3, 8, infinity, or 7, which one's smaller? Well, 3. So I do 1.00 divided by 180.15588 times 6 times 18.01528 and round to 3 significant figures, and I get 0.600. Yay, we just did stoichiometry! So we survived our first stoichiometry. Let's do another one. So for this one, a decomposition of potassium chlorate is commonly used to prepare small amounts of oxygen in the lab. And there's the balanced equation. How many grams of O2 can be prepared from 4.50 grams of potassium chlorate? So here's one hint. Whenever a question gives you one chemical, information about one chemical, and asks you an answer about a different chemical, you know that is going to be stoichiometry, which means you know you need a mole ratio, which means you know you need a balanced equation. So in this case, the balanced equation was given to us. But if in a different situation, you recognize, hey, they gave me grams of this chemical, and then asked me to solve for grams of another chemical, before you try to start mathing, you got to write a balanced chemical equation. So up front, I'm giving them to you. But later, like for example, the example we're going to do after this one, we may have to come up with our own balanced equation. Okay, so let's start with this. So how many grams of O2 can be prepared from 4.50 grams of potassium chlorate? So first we need to figure out, what are we solving for? Well, I want my answer in grams of O2. And then what are we given? What are we starting with? Well, 4.50 grams of potassium chlorate. And then after, in the question, we were given two molar masses, the molar mass of O2 and the molar mass of potassium chlorate. And this is pretty common with how I would do things, because in this question, the point is to do the stoichiometry. I'm testing you less over can you figure out molar mass than I am about the stoichiometry here. Okay, so we have our 3 unit factors. 1 mole equals 6.022 times 10 to the 23rd things, which we use when we're counting atoms or molecules. 1 mole equals the molar mass in grams, which we use when we're dealing with masses. And then the mole ratio, which comes from a balanced equation. So of those 3 unit factors, I know that I need to use the one that has grams in it because I need to cancel out grams. So we're going to have to use molar mass. And more specifically, the molar mass of potassium chlorate. So looking up in the question, we were told that was 122.5495 grams of potassium chlorate in 1 mole of potassium chlorate. Grams can cancel. All right, I know I'm not finished because my unit is moles of potassium chlorate and we're supposed to solve for grams of oxygen. So I know I need to cancel out moles of potassium chlorate, whatever unit factor I choose, because that's the unit that I need to cancel out. Well, of my 3 unit factors, the Avogadro's number 1. I don't care about counting atoms and molecules. Molar mass. I don't want to turn moles of potassium chlorate back into grams of potassium chlorate because I just did that. So it's mole ratio time. So that's going to mean comparing 2 different chemicals from the balanced equation. Well, I know one of them is going to be potassium chlorate. And the other one, well, the answer is supposed to be about oxygen. So I'm going to say moles of oxygen. So the numbers that go in this mole ratio, well, I find potassium chlorate. Well, it has a 2 in front of it, so 2. I find oxygen. Well, it has a 3 in front of it, so 3. So those numbers have to come from a balanced equation. So at this point, the unit left is moles of oxygen. I need grams of oxygen, so I'm not finished yet, but I am going to use molar mass since it is wonderful for converting grams to moles. And I got the molar mass from right here, given in the problem. So I cancel out moles. The unit I have is grams of oxygen. The unit I want is grams of oxygen, so it's time for me to do some work. So sig figs. This has 3 significant figures. This has 7. This has an infinite number of significant figures because they're perfect whole numbers. This one has 6 sig figs, so my answer will have 3 significant figures. So my calculator, 4.50 divided by 122.5495 times 3 divided by 2 times 31.9988. Hit the equal sign, round it to 3 sig figs, I get 1.76. So I would need to make sure that the 1.76 has the unit, grams of oxygen, with it. Because remember, all of our answers need to have a number and a unit. Let's try another one. So propane, which is one of those organic compounds, and I told you you wouldn't have to know its name and chemical formula. So notice I wrote propane, comma, C3H8, I told you what it is a common fuel used for cooking and home heating. What mass of O2 is consumed in the combustion of 1.00 grams of propane? So we are told grams of propane, and we're asked to solve for grams of oxygen. Aren't those 2 different chemicals? And the only unit factor I can use to compare 2 different chemicals is the mole ratio. Do you remember where the mole ratio comes from? Balanced equation. Were we given the balanced equation in this question? Nope. So we're going to have to figure that out. Well, looking at this question, what did they tell us? Well, we know there's C3H8 and O2 in it. See this word right here? Combustion. Didn't we learn something about combustion reactions earlier this chapter? Because we did. It was that you take whatever you're burning, which in this case is propane, and combustion reactions always look like this. Plus O2 gas, arrow, CO2 gas, plus H2O gas. Now we are going to have to balance it. The equation has to be balanced. I'm going to start with carbons. On the left-hand side, I have 3 carbons. So on the right-hand side right now, I have 1. So I'm going to put a 3 right there. I'm going to go to hydrogens next. Remember, I'm putting oxygens last because they're difficult. They're in 3 different places in this equation. So hydrogens, I have 8 on the left and 2 on the right. So I'm going to put a 4 right there. So now it's oxygens. Well, on the left, I have 2. On the right, I have 2 times 3. So there's 6 plus 4 times 1. So 4. So 6 plus 4 is 10. So to get 10 oxygens on the other side, I'm going to have to put a 5 right there. So it'll be 5 times 2. Now that I have my balanced equation, now I can start trying to do the math. Okay, so looking back at the question, what mass of O2 is consumed in the combustion of 1.00 grams of propane? So we're solving for grams of O2. And we're starting with 1.00 grams of propane, which is C3H8. We have those 3 unit factors, Avogadro's number, molar mass, and mole ratio. In this instance, we have to cancel out grams of propane. So I'm going to use the molar mass of propane. That was given up in the parentheses at the end of the question. 44.09562 grams of propane are in 1 mole of propane. Cancel, cancel. No, I'm not finished because moles of propane are not equal to grams of oxygen. I'm not done yet. So I know I need to cancel out moles of propane. And this would be a wonderful time to convert to the other chemical. The other chemical is going to be oxygen. So again, the mole ratio only works for moles. You can't do a gram ratio. That's not a thing. So mole ratio. Once we got moles, now it's time to convert between them. So if we go back and look at our equation, C3H8 is right here. What number is in front of it? Well, I don't see anything, so that means 1. O2 is right here. What number is in front of it? 5. So that's the number that's going to go right there. So I'm going to cancel out moles of propane. Right now, my answer would be in moles of oxygen, which is glorious, but not what I want. So I'm going to use the molar mass to convert from moles of oxygen to grams of oxygen. The molar mass was given. So we can cancel out moles of O2. My units look good, so now it's time to grab my calculator. Looking at my numbers, my answer is going to end up with 3 significant figures. So I'll take 1.00 divided by 44.09562 times 5 times 31.9988, round it to 3 sig figs, and I end up with 3.63 grams of O2. So we've survived some stoichiometry. What I want you to do with this one, I want you to try it. I'm going to give you some information that was not given. Actually, I take that back. What I want you to do is try this, but the first thing, and I'm just going to ruin it for you, there's no chemical equation given. Wait, there's the actual question. There's no chemical equation given. We need to have a balanced chemical equation. So what I want you to do is start by writing the balanced chemical equation. So read the first paragraph. That information, it's going to give you information to figure out what the balanced equation needs to look like, and then you will have to balance it. So hit pause, do that. Once you're done with that, we'll check and see how that goes. Okay, so looking at this, solid lithium hydroxide is used in space vehicles to remove the carbon dioxide exhaled by astronauts. Fun fact, the lithium hydroxide reacts with gaseous carbon dioxide to form solid lithium carbonate and liquid water. This sentence right here is the chemical equation in words. We just have to put it into formula. So we have to take the name lithium hydroxide and write that as a chemical formula. So lithium is Li. As an ion, it's a +1 charge because it's in group 1. Hydroxide is OH-. It's a polyatomic ion. It's got a -1 charge. So as a compound, the +1 and the -1, well, we'll have one of each. It does say up here that it's solid. Reacts with, so I'm doing plus sign, gaseous carbon dioxide. So carbon, 1 carbon, dioxide, 2 oxygen, gaseous, to form, so arrow, solid lithium carbonate. So lithium is Li in group 1, so +1 charge. Carbonate is CO3 polyatomic ion, -2. When I put that together, it's going to take 2 lithiums to cancel out the 1 carbonate. And that's a solid because it says so. And liquid water, so H2O, liquid. Now looking at this, does it look balanced? Well, the lithiums definitely are not. There's 2 lithiums on the right and 1 lithium on the left, so I'm going to start by doing a 2 right here. Now let's count. So 2 lithiums, 2 lithiums. Let's look at the carbons. 1 carbon, 1 carbon. Let's look at hydrogens. There's 2 sets of 1, so there's 2, so we have 2 and 2. Now oxygens, there's 2 sets of 1, so 2, plus another 2, so 4. There's 3 plus 1, 4. Oh, balanced. Okay. So now that we have our balanced chemical equation, let's look at the actual question. How many grams of carbon dioxide can be absorbed by 0.3347 grams of lithium hydroxide? Okay, so hit pause. I want you to try this. The molar masses of what you need are given. So give this a good old try. Like, set it up, and then we'll go through it together. Okay, hopefully you had a chance to give it a shot. So, what did you think we were solving for? Well, hopefully we came up with grams of carbon dioxide. And we're starting with 0.3347 grams of lithium hydroxide. So we need to start by canceling out grams of lithium hydroxide. So the molar mass, which was given, 23.94834 grams of lithium hydroxide on the bottom with 1 mole of lithium hydroxide on the top. So now I have moles of lithium hydroxide. So I'm going to use the mole ratio to convert those moles to carbon dioxide. So looking at my balanced equation, in front of lithium hydroxide is a 2. In front of CO2 is a nothing, which means a 1. Okay. So now I have moles of CO2, but the question asks for grams, so I'm going to use my other molar mass, given. And significant figures, my answer needs 4. 0.3347 has 4 sig figs. This molar mass has 1, 2, 3, 4, 5, 6, 7 sig figs. Mole ratio is infinity. 1, 2, 3, 4, 5, 6 sig figs. So 4 is the smallest. So in my calculator, 0.3347 divided by 23.94834 divided by 2 times 44.0095, rounded to 4 significant figures, 0.3075. Okay. How are we feeling about stoichiometry? Yay! We've got a little bit more to add, but we'll do that in our next video.